Okay, 13, 3. All right, so I don't expect you to know this right off the bat, but just to maybe give me an idea of what you know. How close is the nearest black hole? Soup, salt, the cookie? We're all over the place. It's in our galaxy. We've got one in our galaxy. It is the center of our galaxy. In fact, every galaxy is thought to have a black hole. Every galaxy should have a black hole at its center. That's the current theory, anyway. So yes, there are some not outside of our galaxy. There may be, but we don't know about it. There certainly are in nearby galaxies, and yes, of course, they exist.
So that's on other solar systems. Galaxy and put in nearby galaxies.
So we're going to do a little bit of review of star mass first. What will become of a star with a mass of 2 solar masses? We had a taker on E last time. Maybe we go again?
No.
Somebody put it in there for a while. You're glad I didn't stop the timer. Oh, try it. We'll stop it. We can hit E. Don't push anybody else's clicker. That's just mean. Waiting on one more. Yes. It does what? Well, it will flash red now that it stopped. I think I only got 17 responses. It may not be. Neutron stars. What's the white dwarf limit? 1.4, yeah. 1.4 is the high mass for a white dwarf. So 2 solar masses will end in a neutron star. So just in case you've forgotten, here's a list of the mass ranges for each type of star. Julia, can you sit, please?
I'm trying to.
It's not that hard. It's fairly easy to sit, actually. Given masses in solar masses. So all these masses are in solar masses. I didn't put the units on there. So if you are from 0 to 0.08 solar masses, then you do not create a star. What do we call the result of that thing? A brown dwarf. So that doesn't undergo fusion. It never creates a star. We give that the name of brown dwarf. If you are between 0.08 and 1.4, then you become a white dwarf. So you go through the HR diagram from the main sequence to a red giant, perhaps on the horizontal branch, planetary nebula, and then down to white dwarf in the end, and then you just fizzle out. In what situation would a white dwarf not just fizzle out, but do something more exciting? If there's a buddy star or a companion star, or what we call it in a binary system. If it's in a binary system with another star, it can take mass from it and fuse that mass and undergo novas, and then eventually a supernova if it crosses that 1.4. If it never crosses that 1.4, then it will never supernova. It will just die off as a white dwarf. 1.4 to about 4 solar masses, those will end up with neutron stars. That range is from 3 to 4 from neutron stars. We've seen black holes as low as 3.8, but we're going to call it 4 for the purposes of this class. So if you start with a star with solar mass 1.4 to 4, then it will die off as a neutron star. And what's the final element that the neutron star creates before it becomes a neutron star? Iron. So this doesn't create any elements. This one can create up to carbon, and it dies off as a carbon core. This one creates iron, but then dies off as a neutron core. And if it's more than 4 solar masses to begin with, then that's where we end up with this idea of a black hole. It still fuses all the way to iron, but then it collapses beyond neutron stars. We don't really know what it looks like at the center anymore. But do not forget about this list of solar masses. Okay. Oh, more clear. What prevents a neutron star from collapsing?
See, I got it wrong yesterday. I had, and then in one of the things said neutrons are changed on me, and then it ended up failing everything. I had them all wrong.
No. Nah, sunspots aren't that hot. All right, what prevents a neutron star from collapsing? Neutrons. Yeah, and it says neutron in the question too. That's okay. All right, so on to black holes. So first of all, its mass is larger than 4 solar masses. Now it doesn't go through the progression any differently than the stars that we've been talking about so far. So if you can plot this thing on the HR diagram. It starts as a molecular cloud. It comes down and collapses into. Yes? Yes? Yes, I will. It collapses into a smaller area, then it becomes a main sequence star. It hangs out in the main sequence. Actually, what's wrong with this if we're talking about a black hole? Yeah, it's a big one, so it needs to be up here. So we need to kind of skip this step, and we are supermassive, so we need to kind of go up here. So these black holes are going to come from supermassive stars, maybe a blue star, which gets really, really hot. After it stays in the main sequence for a while, it jumps over to the giant phase, reaches the horizontal branch, and becomes maybe a white giant or a blue giant. And then what happens here? Supernova. It's supernovas. So it fuses all the way to iron like that star would. It can't fuse iron anymore, doesn't get any energy out of that, so it collapses gravitationally. That supernovas and leaves a remaining iron core, which collapses because of its own gravity. It collapses to electron degeneracy, but electrons can't hold it back because it's too massive. It collapses to neutron degeneracy, but neutrons can't hold it back because it's too massive. So this thing is so massive that it's collapsing past electron degeneracy, past neutron degeneracy, and it's actually smashing those neutrons beyond any recognition. It is insanity. It crushes that mass, it crushes that remaining mass into what we call a singularity, which is an impossibly small space. Think of the smallest thing, and then cut that in half, and then cut that in half, and then cut that in half, and keep doing it forever. You eventually come to a point that's just a point. It doesn't have any volume at all. That is what a singularity is. We'll talk more about those later on. We just ran out of ideas. No, and we'll go into why it's not really that proven.
That seems like
Our physics doesn't really work anymore. Yeah, but quantum physics, no, quantum physics doesn't work anymore either. So it really doesn't make any sense. No, we never talked about it. The one difference between this single point in space and regular just points in space, like I can look at, here's a point in space over here, here's a point in space over here, here's a point in space over here, is that this point in space has all this mass. It has the mass of 4 suns, and it's all smashed down into a single point in space. So it still has gravity, just like if it were 4 sun size. So if we could collapse our sun into a small area, then, in fact, you're going to see in a video we're going to show in a second, if we could collapse Earth into the size of a marble, then we would have a black hole. This could be a black hole if it only contained the same amount of mass as the Earth, which it doesn't. Sorry. But it would have the same gravitational attraction as the Earth does. It would just be really small. So the moon could still orbit this. If I put this marble with the mass of the Earth in place of the Earth, the moon would still go around it. The moon wouldn't care. If we replaced our sun with a black hole, we wouldn't experience anything different, except we wouldn't have any daylight or energy or warmth. Other than that, other than those minor things, little chilly.
I think that would actually be a really good solution.
Yeah, sun is a black hole, is a cure for global warming. I think you're onto something. All right. No, gravity is exactly the same because we haven't lost any of the mass, and mass is what determines gravity. So if we replace the sun with a black hole, we would still orbit around it, no problem. 365 days, and we'd still do our normal thing. Of course, if we could get beyond the heat thing, we'd be better off. The term black hole comes from this idea that absolutely nothing can escape it, not even light. So if light can't escape it, then it must be black, right? The absence of light in physics, anyway, is black. In art, it's a little bit backwards. The absence of color in art is what? What color is the absence of color? White. In light is all the colors, yes. So if I don't have any light at all, then that's black in physics. So black holes are so dense, and you can think of it, if something is really heavy, it's really hard to get away from. So it's very difficult to get away from the Earth because the Earth has a lot of gravity pulling it towards you. Let's draw this thing out here. So what determines how, well, let's not do that. All right. Here's the Earth, and if I want to get off the Earth, can I just like shoot a gun straight up and that bullet will go off the Earth? No, because gravity will pull it back. So what do I need to do in order to get off the Earth? How much? Like, is it just like, oh, I can just jump and get out? A lot of speed. We got these massive, we got to get this massive rocket ship, right? At the size of the Earth, evidently. Way bigger than the Earth. Almost goes to the moon, actually. Just walk it.
So that holds it in place.
Yeah, we have this massive rocket ship. We have to travel 4,000 kilometers. Sorry. 4 kilometers per second. 4,000 meters per second. We have to travel 4 kilometers per second in order to leave the Earth. If I shot a gun, it'd be going about 0.2 kilometers per second. It's not anywhere close to going fast enough. And if we got to take like a person off of it, we got to have this huge amount of fuel to carry us off. Well, imagine that if we lived on something more massive than the Earth. Let's say we lived on Jupiter. Jupiter's way, way bigger than the Earth. It's got a lot more gravity. So this number, this 4 kilometers per second, is way bigger. I don't know what it is, but let's say it's 10 kilometers per second. Now let's say we lived on something the size of the sun. Does the sun have a lot of gravity?
Yes.
Yeah, it's holding planets in place. So it has enough gravity that in order to get away from the sun, then we have to go at however many meters per second. Let's say 100 kilometers per second. So the more massive something is, the harder it is to get away from it. Well, imagine something so massive that even light traveling at 3,000 kilometers per second, no, 300,000 kilometers per second, even going that fast, you can't get away from it. That's not swallowing things.
like suck things in.
It doesn't suck things in. It doesn't do anything that Earth doesn't do, except it's way better at doing what Earth does.
Where the idea is like.
So Earth attracts things to it. Like if I was just standing on the Earth and I jumped, I would be pulled back into the Earth. The same concept is happening on a black hole, except in way bigger scale. If I tried to jump off a black hole, it doesn't have a surface for one, but I couldn't even. In fact, I'd just be squished right away.
So.
It's not a surface on it though, so it doesn't make a whole lot of sense to talk about it like that. But.
So if there's not, is it like it's not
Well,
a surface? What is wait?
It's a point in space.
Okay, so
It doesn't have any volume, so it can't have a surface.
there's nothing there, but it's still there's something there. I'm confused. What gives it like the mass to have the gravity?
It is mass. It was mass originally. It was just all that mass combined down into a single point in space.
So it's really small.
Yeah, no, it's infinitesimally small.
Okay, so there's something there. It's just so small that you can't see.
You can't see a single point in space because it doesn't have any volume. There's nothing to see. So imagine here's a graph, a coordinate plane, and we put the Earth on it, or we put the sun on it. And then we take all of this that was in this big space, and we put it at a single point in space at the origin. That a point doesn't have any area. It's a one-dimensional figure. So you can't see it.
I'm trying to make sense of it.
So where did the idea of like that, like those things that come from?
Well, it does have a lot of gravity, so things are gravitationally attracted to it, but in not any differently than a thing is gravitationally attracted to the Earth or the sun. It's just got a whole lot more gravity. Real. Not that much. I mean, it's got huge amounts of gravity, but it's not like well, it kind of is. Everything in the galaxy is going around it because it's gravitationally. Well, okay. So the reason why don't we fall into the sun?
Gravity.
No. No. But we have some velocity that's taking us around the sun, right? We have some inertia that's taking us around. If we just stopped our orbit, if we just put ourselves here, we would accelerate towards the sun and fall into it. The reason we don't fall into it is because we have velocity that's taking us around. So it's the same idea with a galaxy. Everything in the galaxy has some velocity which is taking it around the center. But at that center is a black hole. So it is kind of sucking things in, but nothing, like we're not falling in, well, we're falling towards it all the time, but we'll never fall into it. I guess that's what it is. It's orbit. It's like the space shuttle. It's going around the Earth. It's falling towards the Earth, but it never hits the Earth.
Don't they gravity's like each other? They kind of like control each other in a way? Like they're opposite gravities? Or do they go towards each other?
They would pull towards each other. Now this is a kind of a weird thing. Think of it as once you get close enough to it, you physically leave the observable universe. Now, this is maybe better with kind of an Einstein idea. He kind of gave it the mechanism. So imagine that space is this flat sheet of paper, or this bed sheet, this flat plane. If I put something massive on that bed sheet, let's say I spread out the bed sheet across some tables, and I put something massive in the middle, like a bowling ball. Well, that bed sheet then has a little dip where the bowling ball is sitting, right? It dips down. The more massive the object, the more deep the dip is. So it kind of creates this swell. Let's see if I can draw this a little bit shallow. So if I put something really massive, it kind of bends the sheet down a little bit. It causes it to sag. I can't draw it. I'm not spatial enough to do that. Well, here. Is that better? It kind of sags the sheet down a little bit. Well, imagine that we put something even heavier in there. Well, you'd end up with kind of the same idea here, except now you wouldn't be able to see whatever you put in it because it's sagging down so much. Now think of you trying to climb in and out of this thing. Well, if you've got something that's not so massive, it's not so steep, I could maybe climb out of that. If I had enough energy, I could climb out of it. Well, this one, is it going to be easier or harder to climb out of that? It's going to be way harder because now my hole is deeper. A black hole has a well that has no bottom to it. It's vertical. Can you climb out of a vertical hole? You did. Yeah, you ninja style it, like side to side, like this. No. No. The idea here. Well, the problem is, let's say you fell into this hole. Well, there's not really a bottom, so you can't stop yourself from falling. You're gone. That's why you use a harness. Yeah. All right.
This idea that why does this roll break this?
You can't break space-time. It's a flexible material, I guess. So this is the general idea that the heavier the object is, the deeper the gravitational well becomes. And if you end up taking like a modern physics class, you'll talk about potential wells, which are useful to understand in quantum mechanics. Yeah.
So if black hole is a single point of space, like this dimensional mass, what's behind the idea of black hole taking? Like how
They can get pretty big based on their mass. They have a radius, so there's a certain limit to how big this thing actually is. How big the hole is. And it depends on the mass. So these things can get pretty big if they start with a mass of, say, 100 solar masses. Sorry? Sure, they're theoretically spherical in shape. Well, no, okay, so there's a difference. The singularity has no volume, has no shape. It's not anything. But what we call the event horizon, or the limit to the black hole, has a spherical shape.
So the time it's like that, it's kind of like the center.
Yes. Yes. And then the black hole has a radius around which, if you cross over it, you fall into the hole.
Does that make its area outside of the hole?
Yes, it's a spherical shape, just like a star would be. Okay, good. All right. So I should have been more clear. We're talking about two separate parts of the black hole: the center, which is the singularity, and the shape of it, or the size of it, which is called the event horizon, which is the singularity can't grow. It doesn't have any size to begin with, but the event horizon can get larger. It's like you don't see.
Like in our galaxy, how like there's a black part.
Well, it's not a black part.
Okay, so
All right, so think of the event horizon as the edge of the sun. It's the edge of the sphere, and then the core, instead of having like a size to the core, it's a singularity. The whole thing is the black hole.
so
how do we know the size of
With a three-dimensional ring around it. It's a spherical shape like a star would be, and the center of that is the singularity. This is where all the mass is. This is the singularity.
Can we see the outer ring part as something or no?
We see what's going on around the outer ring part in the form of X-rays. We're going to get into that in a little bit here. So this area, this sphere that's around the singularity, is what we would refer to as a black hole. And this, It does. Not the black hole itself, but the stuff that falls into the black hole. Well, we'll get there. We'll get there. This edge is called the event horizon. All right, let's get into it a little bit. I think. All right. The event horizon is basically the point of no return. So I'm good to orbit a black hole if I want to. If I want to go around this black hole, no problem. Just orbit it like a regular star. But if I get too close to that thing, let's say I orbit and I get right here on the edge and I get past the event horizon, that's it. I can orbit inside of it, but I can never come out of it. I'm stuck. No, I've never tried. Sure. Yes. They were theoretical for a long time, and this wasn't like 50, 60 years ago. People didn't actually believe that. They said, this could potentially be there, but there's no way that could actually be. But now we've discovered basically irrefutable evidence that says this is true, and some of the video will show you. Right. If anything goes across this special area, this event horizon, it's done. You'll never, ever see it again. No. No ropes allowed. There's no ropes in space. Gas. I wouldn't say stars and planets. Things tend to orbit it if they can, and if they get too close, they get shot out into space. So let's say that there's another star that came too close. Well, it came in here. Well, it gets sucked in, and then it gets thrown out like a. We talked a little, or you've hopefully been doing a little bit of research about the slingshot method of space travel. That's what would happen to the star. It would come close, it would speed up and get slingshot, and it would go flying off into space.
Stars stay in that one place, but they approach all the time.
Well, so stars are orbiting this thing, just like the planets orbit our sun. Yeah.
How do they get close? They just like.
Well, if they're not orbiting in perfect circles, then eventually they would get into an elliptical orbit that takes it too close.
The orbit would just be close.
Mm-hmm. Yeah. Right. So once you cross, and if you think about that well, I think it makes sense too. If you think about that well, there's a hole in space here, and once you cross into that little hole, you're done, and you'll never be observed again in space. How is it going to transmit? The fastest you can transmit is at the speed of light. Let's say you can shoot a radio wave back, but this is so massive that not even light can escape. So you could transmit out, but it would never leave the event horizon. Unless you can make something go faster than the speed of light, in which case we'd probably have to revise our whole thing about black holes anyway. Yeah.
So even like waves are affected by the black hole?
Everything is affected by the black hole.
We're affected by the black hole.
We are. We're traveling around the galaxy, so we are affected by the black hole. Ah, but they travel along this fabric of space. And if the fabric is bent, they've got to bend with it. So if you've got a light ray that's coming in here, it can't just go, oh, I got to go around that. No, it's got to go straight, and if it goes straight, it dives into it.
Oh, there's nothing to hold it.
There's nothing to prevent it from going down into the gravitational
So it's
hole.
like a ramp almost, kind of.
Yeah.
Won't be go down it.
Right. It's like those little coin things they've got at the mall where you donate money, it goes around and around and around. Except if you were to throw your coin in there, you could make it kind of dip down and then come out. It doesn't work like that with this. If once it goes in, no matter how fast you throw it, it's going to go down. We mentioned this already, black holes. We can orbit black holes just like anything else we can orbit. So it's just like another star. It's made out of the same stuff, or theoretically it's made out of the same stuff that a star was. It's from a star. It's from a star that went through the same stuff as our sun did, except it's much more massive. When that star dies off, supernova collapses, and that collapse results in a singularity because nothing can stop gravity. if gravity is more than the neutron degeneracy, we just don't know what can stop it. So it just goes down to a single point. That single point has gravity, which affects around to the event horizon and beyond. It affects beyond the event horizon. It's just that the event horizon is the edge of the hole. So you can see here's several different orbits that are coming in. Some of them don't orbit. If you come in with the right speed, you can sit there and orbit it forever, just like the Earth's going around the sun. If you come in too shallow, you fall into the event horizon and you're done. Don't get too close to the singularity. Okay? You guys kind of getting a feel for this, maybe a little bit as much as you can think of? It's all based on gravity. Every single thing about these black holes is gravity-centric.
Wait, so